Hey, everybody, we're back. Thanks very much to Bill Hines from GTech for his presentation. And I'd like to introduce our final speaker, Ryan Schultz from Stanford. After Ryan's presentation, we're going to take a 5-minute break, and he will join a panel titled Tackling Induced Seismicity Risk with Data and Standardization, and hoping we can take some of the learnings from these 3 presentations as food for thought into that panel. So without further ado, take it away, Ryan.
Thanks for the introduction, Jamie. So I'm happy to chat a little bit today about some of the work that I've been doing, trying to think about ways to manage risks related to induced seismicity, specifically doing this in a proactive sense for geothermal energy, EGS specifically, for prospects in the Netherlands. This is work done by colleagues as well, Anne-Marie and Wen Zhou over at U Delft, and associated with the Dutch regulator, as well as my colleagues over Greg and Bill at Stanford. So I don't need to explain this slide, I don't think, too much to this audience. There's a continuing growing need for energy, and specifically looking at different sources of energy, greener sources with climate change and needing to reduce carbon footprint. So geothermal prospects have been something interesting to put into the portfolio. One of the big problems with geothermal, or potential problems, even with EGS type enhanced geothermal systems, are induced earthquakes. There's been numerous cases of this that have happened worldwide. They've been problematic in the sense that they've been large enough in lots of cases to be felt, but even large enough, for example, in Pohang in South Korea, to cause economic loss and injury. Also, a potential risk or a case in point for that is the Basel event, magnitude 3.4 that ended EGS. And in the Netherlands, there's also been up to magnitude 1.7 events that have happened there so far. So for some motivation, there's this clear need for effective and transparent management of this problem. And we're not working in a vacuum here either. Previous experience with induced seismicity at the Groningen in the Netherlands, with an event at the Huizinga, the Huizinga event, a magnitude 3.6 event, has caused the Dutch people to essentially decide to abandon this resource. So stranding some 800 billion meters cubed of gas. So there is this clear need for effective and transparent management of the induced seismicity problem, even specific to the case area that we're going to look at. So transitioning into what do we do about this? One of the de facto means for managing induced seismicity risk is through something called the traffic light protocol. Typically how these work is when you're in green light territory, the operator is allowed to do as they see fit until we grow in magnitude into the yellow light territory, where we start getting earthquakes, where we need to put in some sort of mitigation strategy to make sure that the earthquakes don't continue to grow in magnitude and frequency until we get to a red light point, or hopefully don't get to that, where some sort of regulatory intervention happens, and then we talk about shutting down the operation. So this immediately brings up a question, though, is how do we pick these thresholds, and how do we do it in a way that makes sense? So we've been working in the last little bit to do this in a way that's probabilistic and risk-informed. Risk-informed being important because these are the things that people care about and value. So we can use that to tie back to these risk-informed pieces, and doing it probabilistically to encounter or appreciate all of the variabilities that go into this approach. What we found from this is red lights typically tied to nuisance and damage, your risk metrics that you could be interested in, and then the yellow lights are going to be tied based on a band below what that red light threshold is. So we first did this for zero-dimensional toy models, but have expanded this to real data, which I'm going to talk about a little bit here. So for the workflow of this, we start with something like the spatial area of where we think we're going to be doing the operations. Maybe there's some boundary, geological boundary, where we know we're bound into. And as well, we'll have the geothermal gradient in an area that we can use to constrain what the depth of the operation could be, or doing this for potential siting of operations. This also constrains the depth of the earthquakes. They typically occurred near the stimulation interval, sometimes a little higher, typically a little bit deeper than that. The other piece that we pull into this is we need to know how big the earthquakes can be. I won't go into this because this is the focus of an entire talk in itself. This concept of trailing seismicity. So if we set a red light at a certain threshold, what will be the magnitude, or what would we expect the magnitudes to be that occur after we turn off the pumps. Taking all of these concepts together, we can start building scenarios of where and how big the earthquakes are going to be. And we can use those scenarios for where and how big they are and combine them with ground motion prediction equations, as well as site amplification information to get ground motion shaking scenarios. So essentially forecasting or building scenarios of what we think the hazard could be given these inputs. But we want to transition this into risk. So we have exposure, where people are, the population density, as well as we can pick certain risk metrics. So we're going to think of things like nuisance, the number of people that will feel the earthquake, damage, the number of homes that are going to be impacted by the earthquake, as well as local personal risk, this LPR, which is a chance of fatality from building collapse from the earthquake. Now this approach is a little bit convoluted, so I'll try and repeat it one more time to be clear on what I'm saying here. Is we take a hypothetical operation at a given location. We can constrain the depth of that based on where we're going to be stimulating that based on geothermal gradient in an area and pick an isotherm. We can take something like this trailing seismicity model, which is going to give us the magnitude of events that can occur after we turn off the pumps to give us, for that given epicenter location, the amount of shaking that's going to occur falling off radially away from that epicenter location. We can then combine something like these nuisance functions, which is a chance of nuisance, a probability as a function, or the intensity of the ground motion. And we can see that that's going to change based on what degree of nuisance we're interested in, either just felt nuisance, an exciting amount of nuisance, or frightening levels of nuisance. And very similarly, we have something for the fragility functions, for the damage that might be encountered, which is a chance of damage as a function of the ground motion, for damage state 1, which is cosmetic damage, all the way up to damage state 4, which is building collapse that we're worried about. So if we know at a given location what that ground shaking is, from these functions, we can also estimate what the chance of being felt or chance of damage is. And if we also know where people are at those locations, then we can count essentially how many people are going to be impacted by these things. So that's what's shown here as our final output on this. I'm going to call this a risk curve, which essentially shows that you're getting more risk as you stop at later red light thresholds. You'll notice though that this is a distribution of curves. We do this in a Monte Carlo fashion so that we take into account all of the input pieces or the variabilities in them to get what that variance could look like. So this is the basic concept. With this, we can start pulling in real information, and this is what we did for the Netherlands. So we took an isotherm of 120 degrees Celsius. We can use slope-based proxy for VS30, a type of site amplification measurement. We can use regionally, so there's a number of information that's already available for the Netherlands because of the earthquakes that happened in the Groningen. So we can take regionally calibrated GMPEs, vulnerability functions, fragility functions, as well as regional databases as where the people are located, essentially. And we can use this approach then, and we can say something like, if we chose a magnitude 3.0 as the red light, what would the nuisance, the damage, and the LPR, that chance of fatality, look like as a function of space? And what we see is that essentially where people are most concentrated, you're going to have the most amount of risk. So in the highly populous area, for both the nuisance and damage metrics, we have the highest order, most amount of damage and nuisance that could be impacted, but it changes spatially by orders of magnitude. So as we move into less populous areas, we see that decrease for both of these metrics. So this immediately brings up a concept or a thought process, is if we have 3 different locations, but we pick one single stopping magnitude, what we're going to see is that risk is going to be spatially heterogeneous. It's going to be different for each of those 3 locations. A different way to think about this, so that's going to be what I'm going to call isomagnitude approach. You just pick one magnitude for a broad area, use that. The other way you could do it is an iso risk. So you pick one tolerance for risk that you're not willing to exceed. And if you can agree on that, then you can work backwards to find out what the different magnitudes need to be for the locations based on all this information that goes into this risk-based approach. Of course, that brings up a more difficult question, risk tolerances. How do we pick this? And how do we pick what types of risks? For something like LPR, you can maybe argue that this is something where there's already health standards, where you can look this up essentially in a table, as well as the Groningen committee had already agreed on essentially Dutch tolerances for LPR risk, fatality risk. So you can just use something like that. Something like damage is also a little more straightforward. You could do a cost balance, for example. What's the cost of losing this operation versus the damage that could occur? And you could balance that simply, or you could build this in a way where you just want to avoid damage. These are value-based choices that could be made. One of the more interesting ones that I think needs to be taken into account more seriously is the ability, thoughts around nuisance. So how many people are going to feel this? And you could maybe make some bureaucratic choices around being consistent with blasting criteria in an area, or prior art essentially about laws or legal requirements. I'm an observational seismologist, so I like doing something that's a little bit more empirical instead. So one of the things that you can do is do a calibration. We can look at, because we're not working in a vacuum here, there's been previous induced seismicity. We can look at the 2012 Huizinga event, the event that ended operations in the Groningen, and compare it to the second most impactful event that occurred that was induced seismicity, the 1997 Roswinkel event. Huizinga shown in the red, as then the Roswinkel shown in the green. We can use this as an archetype of an intolerable amount of risk or nuisance and a tolerable amount of nuisance, because this one didn't change anything. And somewhere in between has to be the Dutch tolerance, or we're going to make an argument that the Dutch tolerance for nuisance has to be somewhere in between this, which we can pick just at something like the P10 distribution on that and use that as the threshold. For then, what we can do is we can use that threshold to work backwards, then use that as the tolerance to risk, and use that to figure out essentially what the ISO, or what the magnitude has to be in this ISO nuisance concept, which is just shown here. So it's analogous in that you have to stop at lower magnitudes in populated areas, and as you move to less populated, you can have a little bit more leeway in that. But we're not just going to be interested in the nuisance risk, we're going to be interested in nuisance, damage, and that fatality risk. So we can combine each of these concepts by just looking at each grid point on this map and taking the lowest between each of these three different types of risk, which is shown here. So this is that composite combination map with a controlling factor shown in this. And what we see is that typically in these areas, nuisance is the controlling factor. Now these are the results. We can use this to start answering questions about these operations that we might have. So for example, we could do a hypothetical operation that occurs right on top of the Huizinga event's epicenter. So if we did an EGS operation there and we did it in this way, these are the risk curves. Blue shown for the nuisance, orange is shown for the damage, and then green for the fatality risks. Normalized on their tolerance thresholds for each of these. What we see is that we need to think about stopping at somewhere around 2.5 for our red light for this. Despite the fact that this was calibrated on the Roswinkel and Huizinga events, which are somewhere up around 3.5. This can dominantly be understood as trailing seismicity. So you need to stop before, because it's going to take a while for your operations to typically die down and account for that. The other piece is we need to look at multiple metrics, because if we only looked at something like local personal risk, and we calibrated just on that, then we would expect more, almost an order of magnitude more nuisance and damage risk than the Huizinga event itself. An event that already essentially ended an operation in the Groningen. The last piece that I'll just briefly point to is looking a little bit at these justification for using these metrics and tolerances. I think that we need to use multiple risk metrics, so that fatality risk is obvious and important, as well as damage, but also this nuisance piece. And I think the ability to take this and then do these sort of calibration studies where we look at these things, we can get something like an estimation for what the nuisance tolerance for the tolerance for nuisances in the Groningen in the Netherlands, but we could also have already repeated this approach, looking at frac-induced seismicities for petroleum fracking. And we've seen that this can vary spatially. So likely something like Oklahoma has more risk tolerant to these types of risks versus somewhere like British Columbia in Canada or Alberta, where they've taken more risk-averse choices than this. So we can start using at least these ranges to start calibrating based on this and thinking proactively. For example, trying to get a better sense of what the social license to operate is in these jurisdictions. And with that, I look like I'm running low on time here. So I'll just summarize. We produced impact scenarios for what risk could look like for Dutch induced seismicity, and we've calibrated these tolerances to previous risks for induced seismicity cases, and found that you need to look at multiple different risk metrics if you want to build something, or we are arguing if you want to build something that's a little bit more holistic for red light dots.